Hello, everyone. I wanted to follow up with our discussion board from this week, specifically on the two questions that had to do with the determination if a correlation coefficient was significant or not. And the reason why I want to follow up on this is because from here on out, many of the tests we're going to look at will utilize tables such as the correlation table, well, actually the t-test table for correlations, but it will utilize tables like that where we're going to need to go and check to determine if our obtained value exceeds the critical value to determine whether or not we have statistical significance. So I'd like to go through this in a little bit more detail just as a follow-up. Well, first of all, most of you got the definition of correlation. Correlation is basically determining if one variable is related to another. And that part is related is very important because as we've discussed, and as I discussed at the end of this presentation, correlation is not causation. And so it's very important that we realize we're looking at the relationship. We either have a positive relationship, which means that the correlation coefficient is anywhere from 0 to 1, or we have a negative relationship, which means that the correlation coefficient is anywhere from -1 to 0. And that, well, that's fine. And the tools, many of the tools that we have will give us a correlation coefficient. We don't really know how important that correlation coefficient is. And that's a little bit of what this presentation is about, actually. Cohen in 2009 wrote an article that basically said if you have a correlation coefficient of 0.2, around 0.2, or the same as opposite or is the same is true on the opposite side, on the negative side of -2, then you have what's regarded as a weak correlation. When you get to 0.5 or -0.5, you're at the moderate level, and when you get to 0.8 or -0.8, you're at the strong level. So it just gives you sort of a gauge of how you can look at correlation coefficients that determine the extent that you're actually getting some level of importance or not. Like I said, it works both ways, both on the positive side and the negative side. And as you know, correlation gives you an R value. And then the other piece of information that you can derive from your correlation coefficient, which is that R value, is your squared R, or your R squared, what they call R squared. R squared is a measure of the amount of variability that one variable can account for in the other variable. So when we say R squared, if, for example, we get a correlation coefficient of 0.4, and when we square 0.4, we would get 0.16, or if we convert that to a percentage, that's going to be 16%. What that allows us to say is it allows us to say that the amount of variability in variable number 2 that can be accounted for by variable number 1 is 16%. That leaves 86% of the variability not accounted for. So what does that mean? Correlations are never a positive one or a negative one. You just never get a correlation that's that high, that's that extreme, unless you're comparing something to itself. So they're all somewhere in between. So a correlation coefficient of 0.8, that's considered by Cohen's article to be a strong correlation. And we would look at that and think, yeah, that is a strong correlation. Those two variables are very closely related. But when you do the math on it, you calculate a squared R, or R squared, you realize that that only accounts for 64% of the variability. So we can say that variable 1 can be tracked and can be shown to account for 64% of the variability in variable 2. The problem is that leaves quite a big window of difference where something's going on in variable 1 and there's really no impact in variable 2. So that's why the R squared is kind of important. While we might get a really high correlation, we may not really get a high correlation that means as much as we think it does. And it also sort of points out the kind of an inherent weakness in using correlation as a statistical tool in determining the extent to which two variables are related to each other. There are other stronger tools, but when there's no other, correlation can work just fine. One of the things that we haven't really talked about, we don't often talk about actually in correlation, is whether or not a correlation coefficient is significant. And that really can depend. I mean, we can take two sets of 10 items and we can calculate a correlation coefficient between those two sets of 10 items. But because your sample sizes are so small, that may not have really any significance relative to the list of items themselves. So whether or not something is significant is really going to depend first on what the correlation coefficient was. It's going to also depend on the p-value threshold, what we set to be the p-value threshold, and we as the researcher get to decide that. It's going to be set or depend on the degrees of freedom. The degrees of freedom is really going to be derived from the sample size. So if in my previous example, we're looking at a sample size of 10, that's a pretty small sample size and it's going to yield a small number of degrees of freedom. The larger the degrees of freedom, the more confidence we can have in the result. It's also going to depend on whether we're going to run a one-tail or a two-tail test. And lastly, it's going to depend on what the critical value is. I'm going to go through each one of these now and explain each one in detail so that you have a better understanding of how we determine significance in a correlation coefficient scenario. Is the correlation coefficient. And there are very many ways that software can calculate a correlation coefficient, and you can also calculate it manually, but why would you? You can go into Excel and use the Correl function to calculate your correlation coefficient. When you do that, you're going to get one thing actually from Excel. You're going to get the R, the correlation coefficient itself. You can manually calculate the R squared just by multiplying the correlation coefficient by itself. The p-value threshold is something we determine. So most of the time we're going to probably use 0.05 as our p-value threshold because remember that gives us a 95% confidence level that we are dealing with data that are truly significant, and there's a 0.5 or 5% chance that the data that we got is purely by error. There's no real meaning to it. We could also be more stringent if we want and set our p-value threshold to 0.01, which gives us a 99% confidence level that the data we're dealing with is really significant. Again, like I said, it's up to the researcher. And the reason why this matters is because whether we're looking at it at the 0.05 or 0.01 level, we will get different critical values from the table that we look at the end to determine if we have significance. Degrees of freedom are a little harder to understand. And so I'm going to do kind of a scenario to sort of explain why we use degrees of freedom. Now, degrees of freedom are really about the sample size. So that's kind of the primary goal it has. It's just how big is your sample size? How much data are you depending or are you using to determine this correlation coefficient? But we do something funny when it comes to correlation coefficient in the sense that we reduce the degrees of freedom by 2. Why do we reduce the degrees of freedom by 2? Well, let's see if I can come up with a simple way to explain that. So imagine we have an N of 30. So we have 30 respondents or whatever. And we're running a correlation coefficient between variable 1 and variable 2. In our context where we have 30, there are really only 28 ways that variable 1 and variable 2 can differ. Why is that? So let's imagine we take away 28 of our sample and we're down to 2. If we're down to 2, we know exactly how variable 1 and variable 2 are going to relate to each other. There's no variability left. So that removes 2 degrees of freedom, because when we do that, we've got all these other variables that are these degrees of freedom that can change and vary and whatever. But when we reduce it down to 2, there's no more variability. So that's why we remove 2 from the number of the sample size in order to get our actual degrees of freedom. And this really, when you get down to it, it's pretty precise. The difference between 30 and 28 degrees of freedom, as far as the critical value, is probably not going to mean that much. But it can get down to precision that is meaningful in certain statistical tests. One-tail or a two-tail test? Well, this gets down to kind of the actual test itself. So whether or not we run a one-tail or a two-tail test is determined by what we are looking for. So if we could imagine that we're fairly certain that variable 1 and variable 2 are positively correlated, and we really don't think that there's any chance that there's going to be a negative correlation, then we can run a one-tail test because we're only looking at the positive direction. On the other side, if we are pretty sure that the two variables that we're looking at are negatively correlated and we don't see really any chance of there being a positive correlation, then we can look at the one-tail test again because we're just going to be looking in one direction. But if we don't really know if it's going to be positively or negatively correlated, and whatever result we get, we have to test the significance of it, then we have to look in both directions. That means we have to run a two-tail test. The two-tail test is more conservative. It's more conservative because we have to account for variability at both the positive and the negative ends. So really, if you take the 95% confidence level that's associated with a p-value of 0.05, and you say, I'm going to run a one-tail test, then you can have all of that variability be at the one end. However, if you run a two-tail test, then you have to split that variability into two parts, one at the higher end and one at the lower end. And that allows you to have less flexibility, allows you to have less variability in order to get a statistically significant result. So that's the difference between a one-tailed and a two-tailed test. And again, it's going to come down to the particular scenario and the particular correlation when you make the decision as to whether or not you're going to run a one-tailed or a two-tailed test. And the last thing we're going to look at is the critical value. The critical value comes from the table. Now, there are many tables in statistics. Somebody has gone through and fortunately built all these tables for you. You can find them out on the web. You can find them in the back end of any statistics textbook. They're not too difficult to track down. What they are is they're critical values, and they allow you to test significance based on things like, in this particular case, the correlation, one-tail or two-tail test, the degrees of freedom, and what your p-value is. You get all those pieces in common, all those pieces in combination, and you take them to your table, your correlation table, we'll call it the correlation table, and you check to see if in fact you do have a statistically significant result by determining whether or not your obtained value, that will be your correlation, your R value, is greater than the critical value for that particular part of the table. So we'll look at an example here. In our earlier example, we were talking about 30 people being in our study. So if we have 30 people being in our study, then we can have a degrees of freedom of 28, right? Because we're going to remove 2 of them. So, but there isn't a 28 in this table. So we basically go down to the next lowest or the next level that is lower than what our actual number is. So we'd go to 25. All right, so that's why we identify that we're going to use degrees of freedom of 25. There are 3 other pieces of information that we're bringing over. One of this is going to be whether or not we're running a one-tail or a two-tail test. Well, let's assume that we only think there's going to be a positive correlation, so we're going to run a one-tail test. That eliminates the right side of that page entirely. You don't even need to worry about it. Now, the next thing we have to worry about is whether or not we're going to have a p-value threshold of 0.05 or 0.01. And let's just assume that we're going to go with a more liberal p-value and we're going to go with 0.05. So if we're bringing over our correlation and we're comparing it to the one-tailed test at 0.05 for 25 degrees of freedom, our obtained value is either going to be higher than 0.3233 or it's going to be lower than 0.3233. If our obtained value, our correlation, is lower than 0.3233, we do not have significance. However, if our obtained value is higher than 0.3233, then we do have significance. And that's how we determine whether or not we have significance in our correlations. Let's take a look at some of the questions that you were assigned this week. So the information that you were given in question number 1, part A, is where you're comparing 20 women. You're comparing, I can't remember, strength and speed. There it is, right there. The correlation between strength and speed for 20 women is 0.567. Test these results at the 0.01 level using a one-tailed test. So what are the pieces of information that we know? 1, we have a correlation of 0.567. 2, our p-value threshold is 0.01. Our degrees of freedom is n minus 2, 20 minus 2, or 18, and we're running a one-tailed test. So we can go back and look at the table. If we go back and look at the table, we'll see that for 18, degrees of freedom is 18, we're running a one-tailed test. So we're going to be in this column, and our p-value threshold is 0.01. So we're going to eliminate the 0.05 column and just look at the 0.01 column, and we see that for 18 degrees of freedom, the critical value is 0.5155. 0.5155 is the value that we will either exceed or not exceed with the correlation that we are bringing over. Let's go back to our original problem. We see that our correlation that we got is 0.567. So 0.567 is in fact greater than 0.5155, so we have significance. The critical value from the table is 0.5155. It's one-tailed p-value of 0.01 at 18 degrees of freedom. Our obtained value is 0.567. It is greater than the critical value, so it is significant, and that allows us to reject the null hypothesis. Let's take a look at the second one. The correlation between the number correct on a math test and the time it takes to complete the test is negative 0.45. Test whether this correlation is significant for 80 children at the 0.5 level of significance. Choose whether a one-tailed or two-tailed test is the right one and justify your choice. Okay, so what do we know? First thing we know is our correlation is negative 0.45. That makes sense because the correlation between the number correct on a math test and the time it takes to complete it is 0.45. So the higher the number correct, the lower the amount of time it takes to complete it. So our p-value is 0.05. Our degrees of freedom is 80 minus 2, or 78. and we have to determine whether we're going to run a one-tailed or a two-tailed test. So in this particular case, remember, if we think that the correlation is going to be negative, and we really don't need to test if it's negative or if it's positive, then we can run a one-tailed test. And in that particular case, that's what we're going to do. We're going to run a one-tailed test on this one because we're only going to worry about the fact that the correlation is negative, not that it's either negative or positive. We can rule out the positive piece because we already know that bit of information. We're going to take this over, but before we take it to the table, we're going to make a couple changes. The first thing we're going to do is we're going to drop the negative part of the negative 0.45 or 0.45 because we only use absolute values. We're really measuring the distance from zero. So that means that there's only one direction that we need to test. You'll never see negatives in the tables. So variable 1 goes in an opposite direction of variable 2. It's a one-tailed test. We already decided that. And we drop the negative and use the absolute value of 0.45. So we're just looking at that in this test. And we'll notice that there are no negative values in any of the tables, like I had indicated, and that's the case with all such tables. So when we do that, I'm not going to go back to the table. When we do that, we see that, well, there's no degree of freedom that equals 78 on the table, so we use the next lowest one, and that one is 70 is the closest we come. So we have degrees of freedom of 70. For a one-tailed test with a degrees of freedom of 70 and a p-value of 0.05, our critical value is 0.2319. However, the absolute value of our obtained value is 0.45, and 0.45 is greater than 0.3219, and so we do have significance. So that's just basically how we are determining significance for each one of these correlations. We have to, as I've indicated, we'll go back to the first one. We have to take to the table the 4 pieces of information. One, what is the original correlation that we got? Are we doing a one-tailed or a two-tailed test? What is the p-value threshold that we're willing to accept? And how many degrees of freedom do we have? We take all that information to the table and we find that 0.5155 is our critical value and it is lower than the correlation we got. So the correlation we got is in fact significant, and that was the case in both of these. In fact, all 3 of them, in question 1, all 3 parts of A, B, and C, they were all significant. All right, just a couple more things. Just because a result is significant does not make it meaningful. I've already talked about that a little bit, but we might get a significant correlation coefficient of 0.2, but that's fairly minor, it's fairly low. And then if you go ahead and calculate out its R squared, your R squared is going to come out to be 0.04, or if you convert that over to a percentage, it's 4%. So you're basically saying that you've got a significant correlation of 0.2, but in reality, the first variable can only really account for 4% of the variability in the second variable. And that is not meaningful. It's really just not useful. So this gets into this whole concept of, just because we can doesn't mean we should. And statistics has that too. In a lot of cases in statistics, we can come up with a statistical test that gives us a result that has a p-value that shows significance. But when you look at it, step back at it, look at it from kind of a real-world meaningful perspective, it's not that useful. So just because it's statistically significant doesn't mean it's meaningful. And then the last thing, again, I already talked about this, correlation is not causation. Causation means that a change in one variable causes a change in another variable. So, these are very tightly controlled experiments where you take 2 groups of people that are similar in every way, and you make sure that there's no differences, and you make sure that there's no confounding factors, and you change one thing and see that if it changes something else. I mean, it's really tightly controlled. So those kinds of experiments, they're really hard to prove and they're really hard to defend. And there's just too many confounding factors. But the problem is that many researchers, doctoral level researchers in particular, have the tendency to find a relationship between 2 variables and immediately jump to the across what I call the barrier between correlation and causation. They immediately jump to the conclusion that one variable caused the other variable to do something, and that's just not the case. Correlation does not tell you that. Correlation tells you that they are related. That's the best correlation can do, and it's the best most people can do in experiments like this. If you're going to do causation, you're in for a much bumpier ride. There's much more work that needs to be done to prove that causation is truly there without there being any sort of confounding factors. So just be careful when you're using correlation to not state that variable A caused variable B to do something. It's typically not the case, but you can say that variable A and variable B are related and indicate that that's got some level of significance as well. Okay, hopefully that's helpful, and that helps kind of demystify some of the reason why we're using the table this last week, and why we will use tables in some of the weeks to come.